Okay, as part of the discussion of regular expressions within CPD 214, we've been talking about common meta-characters used in matching expressions. So, for example, where we're trying to match some regular expression in some file, we've seen that we can use not only literals, which just match directly, but we could use these special meta-characters to define successfully richer regular expressions to match general patterns of strings. We can match a wide variety with a single finite length regular expression syntax. We can match, in fact, an unboundedly large set of strings that describe a whole, can be characterized by a whole pattern of strings, and that's what the regular expression is really characterizing a pattern. We've discussed most of the common ones, and I'd invite you to watch them if you haven't, but I wanted to provide now in a sort of single video discussion of some extended regular expressions, many of these not supported directly by grep in its normal syntax, but requiring either the -e syntax or the use of egrep, which is just like using grep but with a capital E, in other words, using the extended syntax. So we're going to go through a set of these extended regular expressions which provide additional convenience in defining some common patterns. So the first is this plus. It's a convenience quantifier because we could use the other quantifiers to provide similar semantics. So it matches one or more of the preceding symbol. You'll recall that we had previously defined a metacharacter that matched 0 or more of the preceding symbol, and it was what? Think about it. It was this star character. So if we had dot star, it could match, in this case, it could be any character. So it could match 1 character, 2 characters, 3 characters, etc. But also 0 characters. So if we had D-O star G, it would not only match dog, but it would also match things like DG. So if we want to enforce a single character, at least one match, we could use the plus character instead of star. So here it will match at least one of A or O, and maybe many. And by the way, it could go from A, O, A, O, A, O. It doesn't have to be the same one every time. So here we have DAG, DEG, for example, DAG, DAG, etc. And again, this does require extended syntax. Similarly, a question mark character also requires extended syntax, and this can be used to match 0 or 1 of the preceding symbol. In other words, it's an optional symbol. So here we have DG, but we'll also support DOG for example, but not DOOG. Just either 0 of them or 1 of the O's. Okay. And I want to emphasize that you can compose these things. So you can have D square brackets, AB, N square bracket, begin square brackets, end square brackets, and then question mark, and we'll have 0 or more of those. Okay. Another thing we can do is we can define this quantifier which matches preceding things a certain number of times, between m and n times inclusive. So it matches at least m times, but no more than n times. Okay. So here's a situation where we need to match within Linux.words. We need to be in the right directory as described by an earlier video. AB, so something from A or B at least 2 times in a row, and possibly as many as 3. So we could have AA, we could have AAA, we could have, I'm going to have to check if that's really capitalized in the file. That may be a mistake. Or we could have AAH because it can be followed by H. Now it so happens that all these are AA, but if there were an ABA, that could also be matched. Okay. A further variant of this supports saying exactly M matches, M or more matches, or up to N matches. So here we're doing, 3 or more matches. And you can see here we have some ABABs, etc. Okay. So here we're saying this guy here gets matched at least 3 times. Okay. Now another even sort of something that's broader and more sort of coarse-grained, how it builds things up is this thing that we know from Unix shell as a pipe command, as a vertical bar. And here we're saying we can say match either this expression or that expression. Now here we have a literal dog or cat, but this, I think it says dog right here, that could be a very, very complex expression, and cat could be a very complex expression of its own, and we're matching either one or the other. Okay. Similarly, as a means of sort of abstraction in building up elements, we could have, for example, we can group things together. So this could be treated as a unit. For example, you could have dog or cat, and that could have a star after it, in which case you have dog, as long as if that sequence, you have dog, cat, dog, etc. That would be something perfectly doable. So if we had dog or cat star, for example, it would match any successive sequence of 0. It would match nothing. It could also match, in other words, an empty string, or it could match a dog, or it could match cat, or it could match dog cat, or cat dog, etc. Okay. In some cases, this could be matched more easily with other patterns. For example, this here is matched naturally, but in general we can do much more because these things can be expressions. These things can be regular expressions in and of themselves. Okay. Just see if my yes, unfortunately it's not logged in. Okay. Here's another component of these. So this is something which requires a little bit of thinking. We can have a \n. Maybe I'll stop it here because this one requires a bit more time.